Okay, so this is the second part of my talk, rotational symmetry of mean curvature flows coming out of double cone. And just to remind you that last time we explained mean curvature flow is, we explained what a Brachy flow is, which is a generalization of mean curvature flow, of singular hypersurfaces in particular allows singular initial data. And we talked about the evolution of cones, and in particular, one of the potential evolution is the self-expanders, and then we talked about non-uniqueness of self-expanders, like there could be multiple self-expanders coming out of a given cone, and we drew the picture where we have a double cone, then the cone whose cone angle is sufficiently large, then potentially you have three self-expanders. There's this one, there's a blue one, just a one-sheeted disconnected guy, and then there will be two. There's a two-sheeted disconnected guy, and then there will be two one-sheeted connected catenoidal self-expander. I mean this first one, light blue. I guess this is the thin one. There's what there'll be a fat one. Looks like something like this. Yes, this fat one is stable, and the thin one's unstable. Okay. Okay. Then we restricted ourselves to rotationally symmetric double cones, I guess, whose two connected components lie on different half spaces. And then we stated the result that any smooth self-expander asymptotic to such a cone is rotationally symmetric. Some remarks. And so today, talk about a little bit more on non-uniqueness. And the first thing I would say is that there are non-self-similar evolutions of the cone. Okay, so it's not true that all potential Brachy flows coming out of a cone are given by the self-expanders. In fact, there are non-self-similar evolutions of the cone. So this was first observed by Bernstein and Wan in a paper in 2019. So they were able to perturb an unstable self-expander by its first properly normalized first eigenfunction, and that creates a graph, an entire graph of a normal graph of the unstable self-expander. And using standard parabolic theory, they can produce a flow starting from the perturbed unstable self-expander, and it will flow. It will be a eternal flow that flows into a stable self-expander. Okay. Now this is not necessarily in the classical sense. This is not actually a flow of the cone, because it's it kind of starts from time one. It starts from the perturbation of the unstable self-expander. But what you can do, which I won't go into too much details because it's explained in the paper, but I won't go into too much detail. But basically. I can actually just draw some of this. So basically, if you have an unstable self-expander sigma, then you can look at, and the perturbation is going to be f epsilon of sigma. Is going to be the graph where f epsilon is going to be identity on sigma plus epsilon times f, where f is the first eigenfunction. Okay, so you look at this family of perturbation by of an unstable self-expander by its first eigenfunction. And then you can form, and then by the result of Bernstein-Wan, for sufficiently small epsilon, you produce a, some sort of, you produce a smooth mean curvature flow that, I guess smooth for a short time, and starting from the surface f sigma of epsilon. And we can do is you take a sequence epsilon going from 0 on the right, say, and time translate this back to after proper time translation and rescaling. You can take a limit as epsilon goes to 0 to get an ancient flow in the rescale setting. So in the non-rescale setting, it will be starting from time 0, and that will be a proper that will be a proper non-self-similar evolution of the cone that comes out of unstable that reaches some sort of unstable self-expander, and they will have the same stable expander limit as time goes to infinity. And now, I didn't really specify how to take the limit as epsilon goes to 0 because you have to actually be careful. Because for example, if you take the epsilon as epsilon goes to 0 on this epsilon, without doing any time translation, then you just take epsilon goes to 0. Then obviously your initial surface, which is f epsilon of sigma, converges to sigma, and obviously the unique smooth mean curvature flux starting from sigma is the self-expander. So you don't actually get anything by just taking epsilon to 0. So you have to do time translation and take epsilon to 0 to get these this family of non-self-similar evolutions of the cone. Okay. Now, the point is that there exist there exist other flows that come out of the cone, not just the self-expanders that we've been talking about. And in fact, so we can show a much more general result. So let's see, be a rotationally symmetric double cone with here lambda is the entropy, which I'll talk about a little bit later. And suppose M is an integral, unit regular, and cyclic Brachii flow coming out of C that is initially smooth. That M is rotationally symmetric for all time. So here, the only regularity. So here the two words I highlighted are the unit regular and cyclic. These are kind of technical conditions, but these are conditions that if you produce a Brachii flow by elliptic regularization, they will have this property. So unit regular means that you can apply a Brachii regularity theorem essentially, and cyclic means that it's it means it's boundaryless in the sense of mod2 flat chains. But it's not that super necessary. It's just the point is that most Brachii flows that if you produce by elliptic all the Brachii flows that you produce by elliptic regularization will have these properties. So this actually they cover a good chunk of Brachii flows that we study. Okay, so this says that not only all the this not only says that not only all the self-expanders coming out of the cone are rotationally symmetric, but all these other non-self-similar potential evolution of the cones are also rotationally symmetric. Okay, and moreover, there's this regularity M is smooth away from its axis of symmetry, and if in addition the cone is not just rotationally symmetric, but it's rotationally symmetric and it's reflection symmetric across some hyperplane, which that's perpendicular to the axis of rotation. The M is actually smooth away from the origin, and these are additional results that come from the proof, basically the Hopf lemma that tells you this, not just the symmetry, but also the regularity. Okay, so here on the highlight this the assumption lambda c is less than equal to 2. So in some sense, this is not a full generalization of the expanded result, because the expanded result we don't have this extra assumption, again, which I'll talk about a little bit later. Even for the expander case, because in the expander theorem we don't have we can have arbitrary cones even with multiplicity. That's still true, but here I have to restrict this to a smaller set of cones, and here lambda c is the Coulomb-Nicosia entropy, which is given by the supremum of 1/4 pi rho to the n over 2 of the integral of e to the minus x minus x naught squared over 4 rho. So this is a quantity that measures the complexity of the hypersurface. So it's essentially the supremum over all translation and dilations of the Gaussian area of the surface. Okay, and in particular, lambda c less than 2. What this rule out is a singularity of multiplicity 2. So what you don't really want is not in the proof that you don't want to have a singularity of two planes, two hyperplanes, and that breaks the proof. Okay. And sorry, one thing I didn't mention is that this vector here, 1/4 to the number 2 is just so that the hyperplane has entropy 1. Okay, and some remarks in order. So first of all, the most important remark is that here it really says that let's say be a rotation symmetric double cone with lambda c less than equal to 2. The entropy bound is actually conjectively redundant. What it means is that it's not that our method can deal with multiplicity 2 singularities. It's just that if you're given a rotationally symmetric double cone, as in this form, of this form, then you should automatically have lambda c is less than equal to 2. That's a that's actually a problem that I tried for a while to computationally. I mean, it's just a purely computational problem, but at the end of the day, I couldn't do this. Even in 3D, it seems to be quite hard. Although in 3D, we actually we have some track of the entropy should be, but the point is that given the cone, because it's a purely computational problem, you can you can just run some numerical computation to rule out to verify this bound. But I was just trying to come up with a proof, and it seems to be quite complicated. I don't actually know how to do it. And again, as I said, the cyclicity and the initial smoothness are used to rule out those triple junction singularities, which again, we've said could exist. There exists some smooth self-explanatory ones with triple junctions. So we don't want multiplicity 2 singularity. We also do not want triple junction singularity. And that breaks down because of the Hopf lemma that we're using. Because in the non-smooth setting, we're using a variant of Hopf lemma that works with non-smooth, that works with integral Bragg flow. So, and that in the proof of I guess in the part of the assumption of the lemma is that you don't have triple junction singularities. So here we need cyclicity and initial smoothness to rule that out. And worth noting that this example that we mentioned here of Bernstein-Wendt and the subsequent limits of Bernstein flows with the constraints of Bernstein-Wendt that do satisfy all these assumptions. So they're initially smooth, the unit regular and cyclic. So I guess part of the conclusion is that these flow lines that we constructed are rotationally symmetric. Okay, and just to mention that all these rotationally symmetric results, if you're familiar with the moving plane method, that they're proved by a bunch of reflection symmetry. So there's nothing special about this ON symmetry. You can actually do the same thing for OP cross ON minus P symmetry. And in particular, I didn't say this very formally, but in particular, the cones over minimal surfaces, the Simons type cones, so-called, they also that satisfy the entropy condition. So they also the theorem also applies to those cones. And the conclusion would be that any integral uniregular and cyclic Bragg flows are OP cross ON minus P symmetric. Okay, so finally, let's I'll mention this sketch of proof, and as I've alluded to quite a few times, that we are doing the moving plane method. So one key difficulty, not that I guess difficulty, key distinction is that most of these traditional moving plane method are the classical moving plane method. Say for Kidasuni, Nirenberg, all the paper I've shown on a minimal surface with two ends, and the classical theorem of Hopf and Alexandrov saying that stating that any closed CMC hypersurfaces are around spheres. Sorry, closed embedded CMC surfaces around spheres. It's not true for immersed CMC hypersurfaces. These are all kind of elliptic method, and then they use elliptic maximum principle and the Hopf lemma. But unfortunately, our self-expander, if you recall from the equation, if you recall from this equation, our self-expanders are the self-expander does satisfy elliptic equation, but the problem is that in this moving plane method, you have to do reflections. And you have to do reflection with respect to some affine hyperplane, right? And the problem is that if you reflect a self-expander that's translated, so basically a translated self-expander is not a self-expander anymore. So that's why this elliptic method don't quite apply, but unfortunately we have, what also holds are the same parabolic method. So instead, if you don't actually look at the self-expander by itself, but you look at the flow of the self-expander. Now it's a self-similar flow. It's a simple flow to analyze, but the distinction is that when you reflect that self-similar flow, you still get a flow. You still get a mean curvature flow, but you just don't necessarily get a self-expander back. It's rather a translated self-expander, but it's still a mean curvature flow. So it satisfies the mean curvature flow equation. And in particular, again, very beginning, we mentioned that this graphical solutions have this nice property, satisfy this very nice equation, and this is equation, the quasi-linear parabolic equation that we can apply the parabolic maximum principle and parabolic Hopf lemma to. So that will give us the proof for the smooth case. So this is similar to the groundbreaking paper of Choi, Haselhofer, Hershkovitz that established the mean convex neighborhood conjecture in R3. They have a similar parabolic moving plane method carried out, but for cylindrical ends rather than conical ends. Okay, so here are the philosophy of the moving plane method, which I'll briefly explain. So the rotation symmetry will reduce to a reflection symmetry. And so what you do is you take a look at a hyperplane that passes through the axis of symmetry, which in our case this is, if I can get this, sorry, my drawing is a little bit scuffed here. I really wish I had a pad to draw this, but let's see what this is. So if you look at so this is a hyperplane, let's call this pi 0. This is the pi 0 is a given hyperplane that passes through the axis of symmetry, okay, and you want to move your moving plane from, say, infinity all the way up to 0, which once you get up to 0, you get your reflection symmetry, okay. And the smooth method basically says that the symmetry at infinity and the symmetry and the graphicality at infinity can be upgraded to symmetry and graphicality in the interior, okay. And the only two issues with moving this, that prevents the graphicality and the symmetry to hold. There are two scenarios. If this graphicality stops to hold, then you have the situation in this first graph, where if you reflect things, then things stop being graphical, and then stop being graphical means, for example, the unit normal to the hyperplane is in the tangent space now, and that's the case where you can apply a Hopf lemma. So this is this will be a contradiction. And the other thing is when the symmetry gets broken, that means in the actual proof there's some sort of containment, but basically it means that at some higher than zero level, the reflection touches the bottom part, which is not reflected, but that, because using the parabolic maximum principle, that violates the parabolic maximum principle. But if you so if the touching point, if you write the two solutions of mean curvature flow near the touching point as graphs. Okay, so those are the simple smooth case. So in the proof of non-smooth case, it essentially follows the same scheme. One thing I haven't mentioned is that I said the symmetry and the graphicality and infinity can be upgraded to symmetry and graphicality in the interior, right? I haven't really talked about the symmetry, how the graphicality and infinity is obtained, and that's by a pseudo-locality theorem of Ilmanen. Well, the different versions, but the ones we use are from Ilmanen, Nevitz, and Schulze. The pseudo-locality theorem basically means that along a mean curvature flow, the graphicality scale can be propagated through times. Okay, so that gives you a large compact set outside of which the flow is a graph over the cone, okay, over the asymptotic cone. And I don't know if you're familiar with the minimal surface case, or even the parabolic, even the cylindrical end for mean curvature flow. This kind of corresponds to a asymptotic expansion near infinity, okay, and then that controls you the graphicality. Okay, so obviously the smooth case we're using just the normal parabolic maximum principle and half lemma that are potentially probably classical. Now obviously in general this is not good enough for general brachyflows, and here I will demonstrate. One thing I haven't mentioned is why these non-uniqueness must develop singularities, which I will kind of forgot. So I'll try to explain here. So what essentially happened? Actually, let's go back. Let me explain here. Sorry for a little bit messy organization. Let's go back here. So I want to say that I want to explain this highlight here. Oops. That these flows must be treated as brachyflows. They were singularities potentially. So what happened is that as we said, better place here. As we let's try like a slightly fatter cone. Okay, as I said, if I have a fat cone, then there's a disconnected guy, which is light blue here, right? And if you can take the innermost connected guy, which is, let's say, yellow, the innermost connected guy, as we said, if I only have three self-expanded, the innermost connected guy has to be unstable. And if you think about it, if you perturb this on one side, especially here on the inside, if you perturb this by the eigenfunction from the inside, and you run this flow that of Bernstein-Wenn, it has to flow into a stable self-expander, and because I'm choosing the innermost connected self-expander asymptotic to the cone, which again this is not. I guess it's not an obvious fact that that there's a Will ordering, but that's a theorem of Bernstein-Wenn. But if you can do that, then it has to move in, right? It had the limit at infinity flows into a stable self-expander. The limit at infinity has to be this light blue two-sheeted disconnected self-expander, right? So at some point, this flow that we produce is going to have like a cylindrical singularity where next singularity where it disconnects in order to flow to the disconnected guy. Now, what I said is not necessarily it's only for the flow constructed of Bernstein-Wenn. It's not for the ancient flows that we have to take the limit. Now, you can use a similar limiting process to deduce that because the limiting self-expander is the same. It still flows into the light blue disconnected self-expander. There should be a discontinuity at some point during the flow in order to they have to disconnect. Now, to make this rigorous, it's kind of there are a lot of things that you have to take care to, especially there's the issue with genericness or not genericity that you have to take care. So the actual argument why these flows have to develop singularity is a little bit longer than I would hope for, but you can show that these flows do develop singularities. So in that case, we cannot treat them as smooth mean curvature flows, but we have to treat them as integral brachy flows. Okay, and that's why in this more general case, the smooth parabolic maximum principle stops to work. If you use the old method, because I have this initial smoothness assumption, I can argue that this flow will be rotationally symmetric after the first singular time. But obviously that's not too satisfying. So we have to find the new method, and this new method again relies on the recent breakthrough of non-smooth parabolic moving plane method. Again, of Choi, Hasselhoff, Hershkovitz, and White. So this is the big paper that proved the Minkowitz neighborhood conjecture in arbitrary dimension. So that's a generalization of the older paper, and they have a non-smooth version of parabolic maximum principle, which we also use. And the second paper of the Hasselhoff, Hershkovitz, why that's in like an elliptic variant of this non-smooth moving plane method. Okay, and finally, in this non-smooth setting, the maximum principle of brachy flow, let me just say that still holds, and part of that is you still need to. So this maximum principle of brachy flows, I kind of mentioned in a second, but it does need the assumption that there's no multiplicity to singularity, and that's where the entropy assumption comes in. And it's not just for two brachy flows. It's like it has to be one brachy flow, and the other flow is actually like when you do the maximum principle, one of them can be a brachy flow, the other of them has to be smooth. But again, the smooth in infinity is guaranteed by zero locality and initial smoothness. So when you come down from using the moving plane, you come down at the top part, you always have smoothness, right? So that's not a big issue. Well, provided you have an entropy bound again. So what we really need here is a suitable substitute of Hopf lemma. So the Hopf lemma is really, I guess, the key to prove all these theorems. So I stated here the key theorem of Choi, Hasselhoff, Hershkovitz, and White about this non-smooth Hopf lemma, which again it's called a Hopf lemma, but the theorem statement doesn't really read like a Hopf lemma. But so let M and M prime be two integral brachy flows define some parabolic ball, where the center X is in the common support. So and suppose X is a tame point, which is a technical condition again, and this is where we need to rule out the triple junctions. So this tameness assumption is where it does not allow this triple junction singularity that we've been talking about. So that's a technical condition, but I want to explain what this is. So suppose X is a tame point for both M and M prime, and you have an open half space with the X coordinate lies on the boundary of the half space, and if the boundary of this half space is not a tangent flow to either of the brachy flows, then you have that the two flows are disjoint in some past times for some T naught minus R squared T naught, then the two flows are smooth at 0, 0 with distinct tangents. Okay, so distinct tangents is kind of like the Hopf lemma part, right? And everything else is kind of more like technical assumptions. So in our applications, this first assumption, if in addition partial H is not a tangent flow to either M or M prime, can be actually is not really a problem because the flow is really irregular, so you have regularity theorem. So if partial H is a tangent flow to either M or M prime, then these flows are automatically smooth. Okay, and the regularity being distinct is also not too big of a problem because if they're not distinct, then you can actually apply the maximum principle to deduce they're the same. So that's also not too big a problem. So really the technical issue here you have to verify is that the flows are tame, which again is some condition that I wouldn't go too much into. And the striking effect of this conclusion is that the M and M prime they don't just have distinct tangents, they also smooth at the 0, 0, and that's where if you think about it, that's where our conclusion come from. So in our application, this H will be this partial H will be the moving plane, right? So basically, basically, where the plane moves through, you would not only deduce symmetry, you also deduce smoothness, even though your flow can be very bad, a priori. So the only place where the plane does not sweep onto is at level 0, which is on the which, if you take the union of all these planes, the only planes where these do not sweep onto is the axis of symmetry, right? That's where this conclusion and smooth away from the axis of symmetry comes from. And again, and the same thing happens here. If you have additionally you have O(n) cross O(1) symmetry, then you can also run the moving plane in this O(1) direction, and that forces the actual non-smooth region to be on the origin. Okay, so that's where I guess that's a quite powerful theorem. And knowing this this maximum principle and this maximum principle of Brachy flows and this Hopf lemma, the substitute Hopf lemma for non-smooth Brachy flows, we get the two same pictures, except here not only graphicality and symmetry are upgraded from infinity to interior, but graphicality, symmetry, and smoothness, regularity are upgraded from infinity to interior. Okay, so that's the I guess difference. So yeah, with these two theorems, then we can proceed as before with our moving plane method with some extra care in technicality than we deduce the more complicated version of the theorem. Okay, and that's everything I have, and thank you very much.